Now, free body diagrams aren't always just going to have arrows, because eventually in physics we have to break it down into math. You may have heard the equation F equals ma, or you may have seen it before, but this is helping us figure out how much of that F we're dealing with. Okay? So I've put some numbers onto these, and these are newtons, which is our measure of force. Sometimes you'll see kilonewtons, sometimes you'll see prefixes on this, but a newton is the basic unit of force that's in that equation. So sometimes you will see arrows, and sometimes you will see newtons, and a lot of times if people are writing the newtons, they won't make those arrows different lengths to show the magnitude anymore. Sometimes they will, sometimes they won't. I didn't hear because I just want you to know to look out for the numbers. If it has numbers and arrows, trust the numbers, not the size of the arrow. Now remember that free body diagrams are a tool for finding net force. And in our last examples we looked and we could tell is there net force or not, but we really couldn't tell how much net force there was. In these examples we're going to determine how much net force there is, and what I hope is a simple way. On example A, I have net force, I have 5 newtons pointing down and 2 newtons pushing up, and some of you may jump the gun and see what the difference between those two is, but I want to kind of lay it out simply. So I'm going to draw 5 arrows representing the 5 newtons of downward force to kind of show you how these cancel out. And I drew those in red so they would match the force that they are. I'm also going to draw 2 arrows of the blue force because there's 2 newtons. There are 2 newtons there for that force on that object. Now, we still have to think about, are these parallel? We still have to think about, are these opposite? Because only opposite arrows, opposite newtons, can cancel each other out. So this is down and this is up. Those are opposites, so they'll cancel each other out. This is down, this is up. Those are opposites, so they'll cancel each other out. And we are left with 1, 2, 3 newtons of downward force. 3 newtons of downward force in this example. So we can see that since this had the larger magnitude, that's going to be what's left over, and that's what we should solve for. If you look at this and it's not going in what is the larger magnitude, then you maybe did something a little wrong. Now the other way to do that is you can set your larger magnitude of 5 newtons up first, and you can subtract or find the difference between those 2 amounts of newtons. Now the trick with this is you need to remember how many newtons were going in which direction, because we can find 3 newtons, but that doesn't tell us much unless we remember those newtons are down. Now, the more correct way to do this, but that you won't always see, and especially won't always see in 8th grade, is to decide one direction is positive and one direction is negative. So usually up will be positive and down will be negative, just like it is on your coordinate plane. So that would say that this is 5 newtons, negative newtons. And Newton's law says the sum of forces, so that means addition. So that's what makes this a little bit more correct. And it's going to be plus 2 positive newtons, since we decided up was positive. 2 positive newtons. Now what's nice about this too is that I don't have to remember that the force is down, because what I'm left with is negative 3 newtons, and I know that negative 3 is my downward direction. I'm not going to go through this math again because we're looking at this as a concept right now, but let's look at example B to see how multiple forces can interact. So I have 5 newtons to the right, so I'm going to draw 5 arrows to represent those newtons. And I also have 2 newtons to the left from one force. And I have 3 newtons to the left from another force. So remember that it's not the color that we're looking at, but it's, are they parallel, which they are. These are parallel lines, so they're going to interact. And then after that, are they opposites, so are they going to interact with each other. So this right can cancel this left, 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 and we are left with no newtons of force left over. So that's 0 newtons. So that tells us that this is a balanced force, which tells us that there is going to be no acceleration. There's going to be no acceleration. Now that's regardless of what the mass of this object is. We know there's going to be acceleration on object A, but we don't know how much without knowing the mass of the object. To do the arithmetic on this one, I'm going to go with our correct way to do it. Usually right is positive and left is negative. It can change those, so be careful. So we have 5 newtons to the positive direction. we have negative 3 newtons to the negative direction, and we have negative 2 newtons in the negative or leftward direction. Now that's just normally how it's done. So remember, this is still a sum. So I'm going to be adding these, even though it'll look like subtraction. So 5 plus negative 3 is 2. 2 plus negative 2 is that. And that gives us those 0 newtons of next force, which has no direction. So it's not going to be accelerated. So we can see that we can add multiple forces together as long as they are parallel. And then we'll decide that they're opposites, just like positive and negatives are opposites. So when do forces not interact? Let's look at that. In example C, looking at our arrows, we have 5 newtons down. Okay, and we have 2 newtons going up from our blue force, and we have 3 newtons going to the right. So we have to ask ourselves, because we kind of have our magnitude of the normal of it, which of these forces are parallel, and therefore we're going to interact. Our red and blue force are parallel, so they're going to interact, but red isn't parallel with purple, and blue isn't parallel with purple, so they're going to ignore each other. So even though there's 5 newtons going down and there's 5 newtons somewhere else, they're not all parallel with the red force. Okay? So we can only cancel out what's parallel. So a down newton can cancel an up newton, a down newton can cancel an up newton, but this is going to leave us with more than one value, which is accurate. We are going to be left with 3 newtons down, and we are going to be left with 3 newtons to the right, which means this is going to be accelerating down and to the right. Now, if we were going to do that in equations, okay, if we look at this, that's positive. It's just 3 newtons. There's nothing to add, so the force to the right is 3 newtons. We do the arithmetic for this one, just like we did for A. But nowhere in this problem would we add those 3 newtons, because they're perpendicular and they therefore don't interact. So that lets us find not only does this object have a net force, but it lets us see how much net force does that object have, which prepares us to plug it into an F equals ma equation and solve for its acceleration if we're given a mass.